Hello, my name is Ken Mitchell, and I am thrilled to present the following slides on AMD Ryzen processors which power today's game consoles and PCs. Let's get started. Today's agenda includes abstract, speaker biography, products, data flow, microarchitecture, best practices, and optimizations. Abstract. Breakthrough CPU bottlenecks to reach higher frames per second and more builds per day, equipped with AMD Game Engineering's knowledge forged through its rich history of partnerships with AAA game developers. Learn about exciting AMD Ryzen products featuring advanced processor and graphics technologies powering today's laptop, desktop, and workstation PCs. Dive into data flow, simultaneous multi-threading, resource sharing, instruction set evolution, cache hierarchies, and coherency. Unlock powerful profiling tools and application analysis techniques using the Windows Performance Analyzer, Concurrency Visualizer, and AMD Microarchitecture. Discover best practices and lessons learned. Upgrade system software and build settings. Attack valuable code optimization opportunities. Examples include C, C++, assembly, and hardware performance monitoring counters. Hello again, my name is still Ken Mitchell. I am a fellow and technical lead in the AMD Software Performance Engineering team where I collaborate with Microsoft Windows and AMD engineers to optimize AMD processors for better performance per watt. In my previous roles, I have worked on optimizing PC games for AMD processors, analyzing PC applications for future product performance projections, and developing system benchmarks. And by the way, just in case you were wondering, this is an image of me holding a metal armadillo. Products. Today's presentation will focus on AMD Zen 4 based processors. Fortunately, many of our recommendations also apply to previous CPU architecture products. Here are some AMD former codename examples for mobile, desktop, and workstation form factors. Not all former codenames for each CPU architecture are shown. Some codename families span multiple form factors. For example, Phoenix was designed primarily as a mobile product. However, Phoenix also scales up to the Ryzen 8000G series desktop products. The AMD Ryzen 8040 series mobile processors, formerly codenamed Hawkpoint, are built on the cutting-edge 4nm process node delivering up to 14.5 hours of video playback. Not only do these processors include powerful Zen 4 cores, but they also include the highest performing integrated graphics you can get thanks to RDNA 3. Better yet, they support Microsoft Windows Studio effects powered by AMD Ryzen AI, our neural processing unit. AMD is committed to years of future support for its Socket AM5 platform, packed with state-of-the-art technologies such as high-speed DDR5 memory, PCIe Gen 5 support, and AMD Expo one-touch memory overclocking. These desktop processors, formerly codenamed Raphael, are also powered by the Zen 4 core architecture. Processors named with the X3D suffix feature exclusive AMD 3D V-Cache technology for a massive gaming performance boost. Additionally, Eco Mode and 65-watt low power models have leadership efficiency. Design, build, accelerate on the ultimate workstation processor. Formerly codenamed Stormpeak, AMD Ryzen Threadripper Pro 7000 series Zen 4 processors deliver battle-tested performance and capability to enable artists, architects, and engineers with the ability to get more done in less time. The TRX 50 platform boasts an impressive capacity of up to 4 memory channels and 48 PCIe Gen 5 lanes, while the WRX 90 platform takes it to the next level with up to 8 memory channels and 128 PCIe Gen 5 lanes. Wow, that's a lot of I/O. Data flow. First, this slide shows an abstract diagram of a Zen 4 based AMD Ryzen 9 8945HS mobile processor, formerly known as codename Hawkpoint, a member of the Phoenix family. Imagine data moving from DRAM on the far right through the data fabric, caches, and cores on the left. Each unified memory controller manages 32 bits of DRAM, DDR5 5600 and LPDDR5 7500 are supported. In this monolithic die SoC design, the orange-colored complex L3 cache connects to the blue color data fabric at 32 bytes per cycle read and 32 bytes per cycle write. RDNA 3 based integrated graphics, a multimedia hub, and a neural processing unit are present in this mobile processor. Some product configurations may feature up to 8.6 teraflops of single precision FMAC integrated graphics performance at 120 gigabytes per second memory bandwidth and up to 16 TOPS of Int8 NPU performance. Next is a Zen 4-based AMD Ryzen 9 7950X desktop processor, formerly known as codename Raphael AM5. Each core complex die in this chiplet design has a unified 8-core cluster with a massive 32MB L3 cache. Each unified memory controller manages 32 bits of DRAM. A DIMM is composed of two 32-bit subchannels. DDR5 5200 JEDEC is supported. Faster memory speeds are possible using AMD Expo technology. Some product configurations may feature up to 1.1 teraflops of single precision FMA integrated graphics performance at 83 GB per second JEDEC memory bandwidth. Thus, the included RDNA 2-based integrated graphics are for basic desktop and office use. We recommend a discrete graphics card for gaming. Finally, we have a Zen 4-based AMD Ryzen Threadripper Pro 7995WX 96-core 192 logical processor, formerly codenamed Stormpeak. Thanks to the new WRX 90 platform, this product has up to 8 channels of DDR5 memory and 128 lanes of PCIe Gen 5. You can add many GPUs, NVMe drives, and high-speed networking devices to this battle station. Each unified memory controller manages two 32 bits of DRAM. A DIMM is composed of two 32-bit subchannels. RDDR5 5200 JEDEC is supported. Again, faster memory speeds are possible using AMD Expo technology. Note, RDDR5 provides more memory bandwidth than RDDR4, so we can feed more cores. This topology with up to 12 CCDs is so large that I have shown it in quadrants for simplicity. This product requires a discrete GPU. Microarchitecture. Advances in Zen 4 microarchitecture include a 13% IPC improvement using typical desktop applications, a larger op cache to deliver more ops per cycle, a larger L2 cache, an improved load store unit with a larger load queue, branch prediction improvements with larger branch target buffers, and AVX 512 instruction support using a 256-bit data path. To improve instruction throughput, the processor implements simultaneous multithreading. Single-threaded applications do not always occupy all the resources of the processor. The processor can take advantage of the unused resources to execute a second thread concurrently. Although each thread has a program counter and architectural register set, core resources may be shared while operating in two-threaded mode. The core is in two-threaded mode while its two logical processors execute program threads. If either of the core's logical processors execute the operating system's idle thread, it may return to single-threaded mode. Disabling SMT and system BIOS menu options will reduce the number of logical processors in the system and limit cores to operate only in single-threaded mode. Resource entries such as queue entries, caches, pipelines, and execution units can be competitively shared, watermarked, or statically partitioned while in two-threaded mode. These categories are defined as competitively shared. Resource entries are assigned on demand. A thread may use all resource entries. Watermarked, resource entries are assigned on demand. When in two-threaded mode, a thread may not use more resource entries than are specified by a watermark threshold. Statically partitioned, resource entries are partitioned when entering two-threaded mode. A thread may not use more resource entries than are available in its partition. Resource entries are unpartitioned when exiting two-threaded mode. Caches and TLBs are competitively shared for Zen 2, Zen 3, and Zen 4. For Zen 3, the integer scheduler, integer register file, and load queue have changed from competitively shared to watermarked. For Zen 4, the floating point physical register file has also been changed from competitively shared to watermarked. These changes improved SMT fairness. Software system requirements for recommended CPU and minimum CPU are often from different product generations with differences in SMT fairness, structure sizes, etc. Consider profiling both recommended and minimum system requirements. Zen 4 added GFNI and AVX 512 support. More details are on the next slide. Please note, AMX instructions are not supported. Zen 4 AVX 512 support includes many ISA extensions which may benefit workloads such as light baking, texture compression, and neural networks. AVX 512 FP16 is not supported. AVX 512 VNI using VEX rather than EVEX encoding is also not supported. Use software prefetch instructions on linked data structures experiencing cache misses. Use NTA on use once data. While in two-threaded mode, beware too many software prefetches may evict the working set of the other thread from their shared L1 data and L2 caches. Prefetch T0 and NTA fill into the L1 data cache. Prefetch T1 and T2 fill into the L2 cache, a new feature for Zen 4. For previous generations of Zen processors, prefetch T1 and T2 filled into the L1 data cache. Cache details, including ways, associativity, inclusion policy, and write policy, are described in the AMD software optimization guides. Designing data structures that match hardware prefetcher access patterns may improve performance. The L1 data cache stream and stride prefetchers are my favorites. Stream prefetchers may fetch additional sequential lines in ascending or descending order. Stride prefetchers may fetch additional lines when each access is a constant distance from the previous. The L2 cache also has a stream prefetcher. Additionally, the up-down prefetcher may fetch the next or previous line. This simple example may trigger a streaming hardware prefetcher as it iterates the contiguous array. Similarly, iterating standard vector may also trigger this prefetcher. In our next code sample, 2 strides are detected. Again, iterating standard vector may also trigger this prefetcher. However, the stream and stride code snippets may not trigger a hardware prefetcher if they iterated instead using a linked data structure with nodes scattered randomly across memory addresses. The cache hierarchy has evolved considerably since Zen 1 was introduced, especially for AMD desktop SoCs. Zen 2 increased the L3 cache size and micro-op cache size. Zen 3 further increased the L3 cache size. Zen 4 grew the micro-op cache and L2 cache sizes. Some Zen 3 and Zen 4 products feature X3D technology for larger L3 caches, which are great for gaming. For example, the Ryzen 7 7800 X3D 8-core processor has a single 96 megabyte L3 cache. The AMD cache coherency protocol is MoESI, modified, owned, exclusive, shared, and valid. Instruction execution, speculative execution, prefetching, and external bus transactions may change the cache's MoESI state. Read hits do not cause a MoESI state change. However, write hits generally cause a MoESI state change into the modified state. If the cache line is already in the modified state, a write hit does not change its state. The AMD Zen 4 microarchitecture implements a large L3 cache shared by up to 8 cores inside each CPU complex, abbreviated as CCX. The L3 cache maintains shadow tags for each L2 cache within its complex. Shadow tags determine if a fast cache-to-cache transfer between cores within the CCX is possible. Cache coherency probe latency responses may be slower from cores within another CCX. 2 CCX are shown in this example. For Storm Peak, imagine up to 12 CCX attached to the data fabric. Minimize ping-ponging modified cache lines between cores, especially in another CCX. Here are a few tips. 1. Minimize using read, modify, write instructions. Use a single atomic add with a local sum rather than many atomic increment operations. 2. Improve lock efficiency. Test and set in user spin locks with the pause instruction. Note, this is especially important for Zen 1 based processors. Or replace user spin locks entirely with modern sync APIs. And 3, use a memory allocator optimized for multithreading. The memory manager is a big repeat offender for contention of locking primitives. Try memalloc or jemalloc. Some AMD products have cores that are faster than other cores. AMD calls this feature preferred core. The system bias may describe the ACPI CPPC highest performance ranking for each logical processor. These values are the basis for the get system CPU set information functions scheduling class values in Windows 10 and later for some AMD products. Windows may use scheduling class during thread scheduling. Scheduling class values may change during runtime. Logical processor 0 may not be the fastest core. CCD 0 may not contain the fastest core. Thread affinity masks may interfere with thread scheduling and power management optimizations on Windows PCs. For these reasons, I typically recommend not setting process affinity or thread affinity masks in PC applications. Best practices. While CPU profiling, prefer shipping or test configuration builds over development and debug configuration builds. It is important to keep in mind that development builds may significantly reduce performance and give rise to false alarms that may waste your time. Additionally, collecting stats may pollute the cache, leading you to investigate cache issues in the wrong places. Logging can also create serialization points. Moreover, many debug builds may disable multi-threading optimizations, which can further impact performance. During the investigation of open issues, developers may request changes that enable debug features on shipping and test configurations. However, it is critical to disable debug features before you ship your software. Anti-tamper and anti-cheat technologies may prevent CPU debugging and profiling tools from working correctly, especially while loading and retrieving simple information. Consequently, we recommend creating a CPU profiling-friendly build configuration similar to the shipping configuration, but with anti-tamper and anti-cheat technologies disabled. Add this build as a launch option during development. Remove this build before release. It is important to test the cold shader cache first-time user experience. If the application has a shader cache, make sure to clear it. Remember that the end user might not run the same scene repeatedly as developers do during debugging. The example provided clears the shader caches for Microsoft, AMD, and NVIDIA. After running the script, it is recommended to reboot the system to ensure that any remaining shaders are cleared from memory. Keep in mind that applications and games can have different configurations of shader caches on disk, leading to varying results. Additionally, the GPU vendor and driver versions used can also affect the outcomes. Use the latest compiler in Windows SDK. This ensures you get the latest build and link time improvements. Rebuilding UE 4.27 is much faster on Visual Studio 2022 and 2019 compared to Visual Studio 2017. Some developers have experienced larger benefits than those shown. Also, ensure you're using the latest C runtime optimizations, especially for memcopy and memset. Some Visual Studio 2022 updates improved indexing performance and vectorization. Windows Defender scans can greatly slow down some workflows. Windows 11 enabled the Windows Defender sandbox feature by default, which greatly improved security, but also increased file copy and file compress times. Add project folders to virus and threat protection settings exclusions for faster build times. This system showed a 20% reduction in build time by adding folder exclusions. That said, warning, this recommendation is for personal development systems and not for continuous integration and continuous deployment systems. Putting all this together, using the latest compiler and SDK, with virus and threat exclusions configured on your local build project folder, you can greatly reduce the time spent waiting on builds each day. A binary may have better code generation using AVX or later ISA by using the Microsoft Visual C compiler option /arc AVX, AVX2, or AVX 512. The minimum hardware requirements for Windows 10 include SSE 2. For Windows 11, it's only SSE 4.1. The Windows 10 supported processor list includes AMD products which support AVX but not AVX2. The Windows 10 supported processor list may include products from other CPU vendors which do not support AVX. Enable AVX 512 in development tools such as light baking, texture compression, and mesh to sign distance fields. We observed a 17% performance increase thanks to AVX 512 while using the Intel Embry Path Tracer with ISPC. Audit content. Ask artists to recommend scenes of interest for profiling. For example, an indoor dungeon with heavy occlusion, an outdoor city, an outdoor forest with alpha transparency, large crowds, or a specific time of day. Unreal Engine developers may find some performance issues simply by running map check, especially for issues related to actor shadows. Unity developers may enforce minimum standards using the asset post-processor. Check stats before CPU profiling. If a scene far exceeds its draw budget or has many duplicate objects, especially duplicate physics objects, report the issue to its artists and consider profiling a different scene. Otherwise, you may risk profiling hotspots which may not be hot after the art issues are resolved. Additional considerations may be necessary to ensure the expected GPU is utilized in hybrid graphics platforms. The Windows 10 Spring 2018 update added the enum adapter by GPU preference function. Use DXGI GPU preference high performance for game applications. The user may change preferences per application in Windows graphics settings. Prefer H.264 video and AAC audio codecs as recommended by the Unreal Engine Electra Media Player. Hardware-accelerated codecs may increase hours of battery life and reduce CPU work. Please note, Radeon graphics devices released since 2022 no longer accelerate WMV3 decoding. If you are using WMV3 content, please replace it with H.264 content, which may provide a better user experience. Optimizations. Sync APIs. Avoid user spin locks that starve payload work on other ready threads, consume excessive power, and drain laptop batteries. User spin locks may waste CPU time since the OS scheduler cannot determine if it should yield to another program thread or continue to spin. In this exclusive lock test, user spin lock implementations consumed 100% of a Threadripper 96-core 192 logical processor. However, legacy and modern sync APIs consumed only 5% or less to do the same work. Prefer standard mutex with good performance and low CPU utilization. Modern sync APIs like standard mutex may leverage AMD's mwaitx instruction. This instruction can efficiently wait on an address or timeout. Better yet, it can execute at any privilege level. However, legacy sync APIs like wait for single object may rely on expensive syscall instructions. The syscall instruction invokes an OS system call handler at privilege level 0 from a user privilege level 3 application. Transitioning between address spaces or privilege domains may require additional OS and hardware work. Core isolation memory integrity, also known as virtualization-based security hypervisor protected code integrity, may sometimes lower performance. Windows 11 ships with this feature enabled by default to provide increased protection against malware. Here's the source code for the main function used in the exclusive lock microbenchmark. We will reuse it in the next few slides. Basically, it times how long it took all threads to execute the callback function. Here's an example of a bad user spin lock. This lock may waste CPU time since the OS scheduler cannot determine if it should yield to another program thread or continue to spin. One of the most common traits of a bad user spin lock is a while loop that lacks a pause instruction. Such loops can consume an excessive amount of core resources, performing non-payload work and starving the other logical processor sharing the same core resources. Remember, spin locks can also consume a lot of power. For notebook gaming, this can reduce hours of battery life, make the system uncomfortable to touch, and steal power budget from the GPU. If you decide to use a user spin lock regardless, here are a few tips. Test, then test and set. Add one or more pause instructions, and align the lock variable. Some developers tune the number of pause instructions within the while loop for their target hardware or use an exponential backoff. But beware, CPU time may be wasted unless the spinning thread is eventually put into a wait state. Wait for single object with create mutex are shown in this example. These two APIs have been around for a very long time. The wait for single object function checks the current state of the specified object. If the object state is non-signaled, the calling thread enters the wait state until the object is signaled, or the timeout interval elapses. Thus, wait for single object may not suffer from OS thread scheduling and core resource sharing issues caused by user spin locks. Better yet, standard mutex is even faster than wait for single object. This modern sync API is based on a slim reader-writer lock in Microsoft's implementation, which can be verified using the Windows Performance Analyzer. In my testing, standard shared mutex and intercritical section also outperformed wait for single object. Here's a list of some preferred modern sync APIs which include the efficient mwaitx instruction. Standard mutex acquires slim reader-writer lock, sleep condition variable, and intercritical section. Avoid or minimize functions with syscall instructions such as wait for single object and wait for multiple objects. Windows ships with the Windows Performance Recorder built in. No additional tools are required for users to collect these logs. Install the Windows Performance Analyzer from the Windows Store to open these files. Generally, WPA is the first tool I use when analyzing a system or workload. It is highly configurable with excellent filtering and pivoting capabilities. In this example, we see the improved user spin lock test uses all logical processors at the start of the test. Total CPU usage decreases as threads finish execution. For standard mutex, we see very little CPU usage throughout the exclusive lock test. We can also see there are no other processes consuming significant CPU time. Although not shown in this example, these logs can also be used to analyze thread priority. Because it downloads and caches symbols so quickly, I use WPA at least once before using other profiling tools. Frequently, I use Windows Performance Analyzer, Visual Studio Concurrency Visualizer, AMD Microarchitecture, and Windows Debugger. Warning, observer effect from profiling tools increases as the number of counters and sampling rate increase. Beware user spin locks obstruct synchronization analysis. The Visual Studio Concurrency Visualizer is unable to determine the unblocking stack in our improved user spin lock example. This can hide other multi-threading performance issues such as task granularity or load balancing. Fortunately, the Visual Studio Concurrency Visualizer can determine the unblocking stack in our standard mutex example. Although the current stack is in user code, the unblocking stack still does a syscall into NTOS kernel. More importantly, we can now see worker threads spend most of their time blocked rather than in execution. We can also see a waterfall of serial work. These issues may have gone unnoticed had we used a user spin lock rather than synchronization APIs. Threading. This advice is specific to PCs with AMD processors and is not general guidance for all processor vendors. Profile your game to determine the optimal thread pool size for both game initialization and gameplay. Utilizing all logical processors in SMT dual thread mode may benefit game initialization, including decompressing assets, compiling, and warming shaders. However, SMT and cache contention on the main or render threads may lower performance during gameplay. Tuning the thread pool size based on the number of physical cores may reduce this contention and improve performance. For gameplay, we recommend using the physical core count on systems with at least 8 Ryzen CPU cores. This recommendation is based on our experience and subject to change. Thanks to this optimization, some games increased frame rates by 5 to 10%. Results may vary. A code sample for detecting core counts is available at gpuopen.com. Avoid hard affinity masks on PC. Hard affinity masks represent the only logical processors allowed to run the thread. Typically, these masks interfere with OS power management and thread scheduling optimizations, especially for notebook and heterogeneous systems. Restricting where a thread can be scheduled can harm performance when other PC applications are running, such as browsers, media players, system monitoring tools, and RGB software. These masks can also reduce hours of battery life. APIs using hard affinity masks include the Windows XP function, set thread affinity mask, and the Windows 7 function, set thread group affinity. However, CPU sets provide APIs to declare application affinity in a soft manner that is compatible with OS power management. APIs using soft affinity CPU sets include the Windows 10 function, set thread selected CPU sets, and the Windows 11 function, set thread selected CPU set masks. Avoiding hard affinity masks on PC may improve performance and hours of battery life while gaming. Thread priority describes the order in which threads are scheduled. Each thread has a dynamic priority. The system boosts the dynamic priority under certain conditions such as foreground window change, user input, timer messages, and satisfied wait conditions. My colleagues have observed cases where temporary priority boosted threads switched in before threads intended to be higher priority by the developer. In these cases, the user experience improved by disabling priority boost. The set process priority boost and set thread priority boost functions can be used for this purpose. Data access. Update your compiler for the latest memcopy, memset, and other C runtime optimizations. Memcopy behavior is undefined if the destination and source overlap. However, the compiler may generate rep move string instructions which have defined overlapping behavior. A Linus 64 may allow for faster rep move string microcode. A Linus 4096 may reduce store-to-load conflicts. The processor uses linear address bits 0 through 11 to determine store-to-load forward eligibility. STLI other events in AMD Microarchitecture count store-to-load conflicts where a load was unable to complete due to a non-forwardable conflict with an older store. Additionally, a Linus 4096 may benefit probe filtering on AMD Threadripper and EPYC processors. Finally, aligning to the bit floor clamp between 4 bytes and 4096 bytes may provide a good balance of cache hits and alignment. False sharing may occur when 2 or more cores modify different data within the same cache line. Finding and fixing false sharing issues may have great performance benefits. Common solutions to false sharing in multi-threaded applications include a Linus 64, using a local variable when possible, and processing a range rather than a single element. This micro benchmark showed its execution time reduced by about 90% after optimization using a Linus 64. For this example, each thread accesses a single thread data element within an array. Before the optimization, the array was compact, but unfortunately, different threads frequently modified the same cache line while using their thread data in the callback function. Simply padding each thread data using a lineas of the native cache line size resolved this issue. If and only if virtualization-based security is disabled, AMD Microarchitecture offers a cache analysis profiling feature. Using this tool, we can see the top function hotspots sorted by L1 data cache miss latency. Before our optimization, our function fn is at the top of this list by many orders of magnitude. Microarchitecture can determine the top shared cache lines, including their cache line address, offset, thread, and function. Before the false sharing optimization, we see several threads doing loads and stores to different offsets at the same cache line address. We can double-click on the function name to open the source code view for a deeper investigation. The sources view shows C++ source lines and disassembly of interest. Often modifying shared cache lines may result in high L1 data cache miss latency. The disassembly shows this latency is high at the add instruction before optimization. After our optimization, our function fn is no longer at the top of this list. Use software prefetch instructions for linked data experiencing high cache misses. In this example, performance improved over 60% using software prefetch optimizations. Results may vary significantly for systems with different cache sizes or different memory latency. The NVIDIA Physics Kappa demo iterates a standard vector of pointers. Consequently, the stream and stride hardware prefetchers are of little help due to the pointer chase. Before the optimization, many of the data accesses in the innermost loop missed the 4 MB last level cache of the AMD Ryzen 7 4700G. Since the convex class member data is not public, offset of keywords cannot be used, and thus literal offsets are shown. Although not illustrated in this example, additional performance may be possible by reordering the hot member data to occupy only 1 cache line rather than 4. For Zen 2 and Zen 3 CPUs, there is a significant penalty for mixing SSE and AVX instructions when the upper 128 bits of the YMM registers contain non-zero data. Transitioning in either direction will cause a micro fault to spill or fill the upper 128 bits of all 16 YMM registers. There will be an approximate 100 cycle penalty to signal and handle this fault. To avoid this penalty, a V0 upper or V0 all instruction should be used to clear the upper 128 bits of all YMM registers when transitioning from AVX code to SSE or unknown code. In this example, benchmark execution time was reduced by over 60% after a V0 upper optimization. Thanks to its microarchitecture improvements, Zen 4 does not have this penalty. Use the floating point dispatch faults PMC event to find code which may be missing V0 upper or V0 all instructions during AVX to SSE and SSE to AVX transitions. In AMD Microarchitecture 4.2, this is simply called SSE AVX stalls. Here are 3 simple optimizations which may mitigate this performance issue. First, use the arc AVX compiler flag. AVX is supported by 97% of users according to the January 2024 Steam Hardware and Software Survey. However, this may not be a viable option for software with very old SSE2 minimum hardware requirements. Second, return an M256 value using pass by reference in the function parameter list rather than the function return type. And third, use force inline on the function definition. Any of these changes may allow compiler optimizations to reduce floating point dispatch faults. Here's an excellent example of the floating point dispatch faults issue encountered in the Mesh to SDF benchmark. Both the before and after optimization examples are compiled using the default /arc SSE2 flag. Before the optimization, the function return type is a M256 value. After the optimization, the M256 value is returned using pass by reference in the function parameter list. Using AMD Microarchitecture, we can quickly find the hot line of source code and its assembly code. In this example, the column SSE AVX stalls per 1,000 cycles is greater than 0. Looking at the assembly code, we can see there is a variable blend packed single precision AVX instruction, which is soon followed by a move align packed single precision SSE instruction, where the upper 128 bits have not been cleared by a V0 upper or V0 all instruction. This needs optimization. After the optimization, the M256 value is returned using pass by reference in the function parameter list. Using AMD Microarchitecture again, we can find the same line of source code and its assembly code. We can quickly observe floating point dispatch faults per 1,000 cycles is 0. Awesome! The compiler has inserted a V0 upper instruction between the AVX and SSE2 transition. This performance issue is resolved. Do you want to know more? Discover your best graphics performance by using our open source effects, SDKs, tools, and tutorials at gpuopen.com. Software optimization guides for Zen 1, Zen 2, Zen 3, and Zen 4 are available in the AMD Documentation Hub at amd.com. Got questions? Email us. We'd love to hear from you. This is John. This is me. Those are our email addresses. Design faster, render faster, iterate faster. We can't wait to see what you create.